This lecture is titled YAGNI Principle. The power. People are always looking for ways to make all around them as much powerful as possible. Developers are also people, and they also tend to make all the program code as general as it can be. For example, when a software developer has a task to create a simple library for generating simple income-outcome reports, he will roll out the whole general-purpose library for generating any possible financial reports. I need to parse one key-value pair from a custom binary format. What am I doing? Correct, I'm writing the whole damned parser with handling all the possible cases. YAGNI means you ain't gonna need it. Is all about avoiding over-engineering. YAGNI is strongly related to what we discussed earlier in the course. Do you remember the smell called needless complexity? YAGNI tells us that we should avoid this smell. Do you remember our talk about anticipation of upcoming changes? Anticipating upcoming changes, developers start to introduce points of extension. The problem is that it might happen that all those points of extension will never be used. Points of extension have their cost. They are not free. They make systems more complex, and therefore harder to understand. YAGNI is deeply a philosophical principle. There is no well-defined criterion which allows to measure the YAGNiness of the system. If you look at Wikipedia, you'll see that YAGNI is a principle of extreme programming, or XP in short, that states a programmer should not add functionality until deemed necessary. As a type of agile software development, extreme programming advocates frequent releases in short development cycles, which is intended to improve productivity and introduce checkpoints at which new customer requirements can be adopted. XP co-founder Ron Jeffries has written, "Always implement things when you actually need them, never when you just foresee that you need them." YAGNI is a principle behind the XP practice of do the simplest thing that could possibly work. Another interesting concept, which is also strongly related to YAGNI, is called worse is better, also known as New Jersey style. Regarding software development, worse is better implies a model of software design and implementation which has the following characteristics. Simplicity. The design must be simple, both in implementation and interface. It's more important for the implementation to be simple than the interface. Simplicity is the most important consideration in a design. Correctness. The design should be correct in all observable aspects, but it is slightly better to be simple than correct. Consistency. The design must not be overly inconsistent. Consistency can be sacrificed for simplicity in some cases, but it's better to drop those parts of the design that deal with less common circumstances than to introduce either complexity or inconsistency in the implementation. Completeness. The design must cover as many important situations as is practical. All reasonably expected cases should be covered. Completeness can be sacrificed in favor of any other quality. In fact, completeness must be sacrificed whenever implementation simplicity is jeopardized. Consistency can be sacrificed to achieve completeness if simplicity is retained. Especially worthless is consistency of interface. There is a problem with all the meta principles. The ways we can follow them and apply on practice are vague. The only thing we can do is to discuss the YAGNI in more details, but in the end our discussion will also contain such hard-to-measure things like complexity of software. For example, consider the following sentence from a blog of Martin Fowler. This is a good sentence which makes clearer the meaning of YAGNI, but it's still not so easy to apply on practice. Here's the sentence. If you do something for a future need that doesn't actually increase the complexity of the software, then there's no reason to invoke YAGNI. The complexity of the software. The question arises, how the hell am I going to estimate the complexness? Before looking at a couple of examples of applying the principle, I also want to state that you shouldn't adhere to any principles blindly. For example, if you blindly adhere to the YAGNI, you'll end up with disorganized code and will face sooner or later the necessity to perform a massive rework. So you have to heavily rely on several other practices such as continuous refactoring, continuous automated unit testing, and continuous integration to avoid negative consequences. YAGNI depends on supporting practices, and this is stated in the original definition in extreme programming. Let's consider two cases when we can apply YAGNI. I'll call the first case a high-level one, and the second case I'll call a low-level one. Imagine a situation. A team is working on a payment system which interoperates with many devices, such as coin dispensers, bill acceptors, and so on. There can be many models of any type of those devices. Working on a current version, you need to implement a driver for interoperating with model Z of a bill dispenser. At the same time, a project manager expects that in 4 months they will need to support the Y model of a bill dispenser. It's a temptation to implement that expected model in parallel with the Z model to avoid task switching in the future, and by the way, it would be great to say to boss in the future, "Hey, we've already done it," when the time to implement the Y model comes. Deciding to implement such presumptive features is a classic violation of YAGNI principle. Do you realize the possible financial wastage in the case that model will never be needed to be implemented? The cost of build is comprised of all the efforts spent on analyzing, programming, and testing this now useless feature. Okay, imagine that a project manager was right about that feature. Do you think that there is no cost of such a decision? The thing is that implementing that expected feature, you steal time which could be spent on other really needed features. This is a cost of delay, since other features will be delayed. The delay will be equal to the time spent on implementing that expected feature. And this is not to say that you initially could be wrong and that feature could never be needed. And this is not the end. Another cost of implementing features we anticipate being in demand in the future by using a crystal ball for fortune telling is the cost of carry. Very often, additional code makes a system harder to understand, maintain, and modify. So if you also need to implement a really needed feature which depends on that code related to devices, you'll likely spend more time to implement it. And this is not the end. There is a very unfortunate scenario when the necessity of a feature is correctly forecasted, but the implementation of that feature is wrong. When the time comes and you realize that a feature is implemented not as expected by clients, you'll face yourself in a situation when you have a wrong feature, sometimes completely wrong, and you have to make a hard decision. Whether to throw away the current implementation and re-implement the feature completely from the ground, or to invest resources into the repairing of the existing wrong implementation. This is a very hard dilemma. It's hard to estimate whether you should rewrite the feature or to repair the existing one. Martin Fowler came up with a great scheme which demonstrates all the potential problems related to YAGNI violation. The example we discussed is the high-level case, and YAGNI is much simpler to apply on this level. Though, of course, even at this level, sometimes we make mistakes. Another case is low level, and it concerns everyday choices we make in the process of coding. For example, imagine that right now you're writing a function within a class which needs to parse a number from a custom string retrieved from a plastic card. You basically have two choices. One is to just implement a separate function which passes that string within that class you are working on right now. The second choice, and this is the way we choose by default very often, is to implement a parsing function and extract a utility class which contains that parsing function. This sounds logical since we may anticipate that our colleagues might also want to use the feature of parsing from other parts of the codebase. I don't want to answer this question in relation to this particular case. I want to answer the question generally. There is a simple algorithm which helps to make a right decision in the coding process and in such situations. First, ask yourself if the function or a feature is needed to be implemented right now. If the answer is yes, then implement it. If the answer is no, ask yourself another question. How many efforts will it take to implement that function or a feature in the future in the case it will be required? If the answer is it will definitely be very simple, then keep all the things as they are. Don't introduce anything additional. If the answer is it will take enormous amount of time to rewrite many things to tweak the design to make it enough supple to introduce that feature, then consider to perform some refactorings which allow you to avoid massive rewritings in the future. Remember that neither agile practices nor any meta principles impose the idea to avoid planning. On the contrary, you should always carefully plan what you will need in the future and what resources and efforts will it take from you to meet new requirements. Again, it doesn't mean that you have to perform a big upfront design, but it also doesn't mean that you have to forget about planning. The goal we want to achieve applying YAGNI is to save some time. Please don't apply YAGNI to refactoring. You need to perform refactoring to enable YAGNI. I hope now you better understand how to achieve the Holy Grail with the algorithm I laid out in this lecture. Be ready to fail applying the YAGNI principle. It will take some time to get enough experience, and in the end your perseverance will pay off. In the next lecture, we will take a look at the separation of concerns principle.